Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will discuss complex matrices. So, in complex matrices, we have certain properties and features and certain terminologies. So, what is a symmetric matrix? So, if the transpose of a matrix is equal to the original matrix, then we call that matrix as a symmetric matrix. Similarly, if the transpose of a matrix is equal to minus of the original matrix, that matrix is called as skew symmetric matrix. So, this is the definition of skew symmetric matrix. And if the conjugate and transpose of a matrix is equal to the original matrix, then that matrix is called as Hermitian matrix, right? So what is the definition of conjugate of a complex number? So this is a complex number. A is equal to x plus iota y. Now the conjugate of A is equal to x minus iota y, and the definition of iota is equal to minus 1 square root, which all of us know. And the magnitude of A is equal to x square plus y square under root, and the square of the magnitude of A will be equal to x square plus y square. Now, if we have A as a complex number, then the magnitude square of this A complex number is equal to A multiplied by A conjugate. So, if we expand A multiplied by A conjugate, you will see this is x plus iota y, this is x minus iota y. So, the product of these two complex numbers is equal to x square minus iota y square, and that will be equal to x square plus y square. And the magnitude of A is equal to x square plus y square under root. So the magnitude square of A matrix is equal to the product of A and A conjugate. Now, what is a complex vector? So if the components of a vector are complex numbers, then that vector is called as complex vector, right? So this is our column vector, and the components of this vector are x1, x2 up to xn. If these components are complex numbers, then that vector is called as complex vector. So this is aj plus iota bj, right? X2 will be equal to a2 plus iota b2 and so on. So suppose this is our complex vector, x is equal to 1 iota. Now the second norm of this complex number x will be equal to x with two vertical bars surrounding this complex vector, right? So this is called a second norm. Now, what is the definition of the second norm? So, what is the definition of the first norm? You know that we have a complex vector in which all the components are complex numbers. So if we evaluate the first norm of x, that will evaluate the magnitudes of all the complex components, right? The component, the magnitude of this component, the magnitude of this component, and so on. So after evaluating the magnitudes of all the components, all complex components will turn into real numbers. Now, the second norm will actually convert this vector into a scalar. So that will evaluate the magnitude of this vector, right? So the square of the first component plus square of the second component plus square of the all components and the square root. So that second norm will convert this vector into a scalar number. So again, I will repeat. The first norm will convert these complex numbers or complex components into real components, and the second norm will convert that vector into scalar, right? So if you evaluate the second norm of a complex vector, that will simply give you a scalar number, right? So suppose we have another complex vector in which the components are 2 plus iota and 2 minus 4 iota. Now the second norm of vector y and its square will be equal to the square of the absolute values of these complex components. So first evaluate the magnitudes of these two complex components. So the magnitude of 2 plus iota, magnitude of 2 minus iota, and then evaluate the absolute value and then take the square. That will give you the square of the second norm of y, right? So the magnitude of this first component will be equal to 2 square plus 1 square under root. So that will be equal to 5 under root. The magnitude of the second component will be equal to 20 under root. Now evaluate the absolute value of this real vector and then take the square, right? So the absolute value of this real vector is equal to the square of the first component plus square of the second component, right? So 5 plus 20 whole under root. So 5 plus 20 whole under root, and then you will take the square. So this under root will cancel out with the square. So you will get 25. So 25 is the second norm of this complex vector, right? So another definition of complex vectors or complex matrices is that the square of the second norm of a complex vector is always equal to the conjugate and transpose of that vector multiplied by the original vector. So if you evaluate these two operations and compare your answer, those answers will be same, right? So x bar is actually the conjugate of x. Sometimes it is written as x steric and sometimes conjugate is written as bar. So x is equal to 1 plus iota and 3 iota, right? So conjugate of x will be equal to 1 minus iota and minus 3 iota. And the transpose of this x conjugate will be equal to 1 minus iota and minus 3 iota. So this is the transpose of this vector. Now let's multiply this x transpose conjugate with this original x. So you will get the product of these two vectors, right? And after multiplying these two vectors, you will get 11 as your final answer. Now let's evaluate the second norm of x. So let's evaluate first the magnitudes of these two components. Magnitude of this component is equal to 2 under root and the magnitude of this component is equal to 3. Okay, so the second norm will convert these two components into a real number. So 2 under root square plus 3 square, that will be equal to 2 plus 9 is equal to 11. So both answers are equal. So it means we can conclude that x second norm square is equal to x conjugate transpose multiplied by x. Okay, because we have evaluated the same answers. So now the what is the Hermitian of a matrix? So Hermitian of a matrix is equal to the transpose of conjugate of A, right? So if you take the transpose of conjugate of the complex matrix, that is called as the Hermitian of that matrix. So A Hermitian is equal to A conjugate transpose. So the Hermitian of this matrix will be equal to, first take the conjugate. This will become 2 minus iota minus 3 iota 4 plus iota 5 0 0. Then take the transpose. So this matrix is 3 by 2. So the transpose of this matrix will be 2 by 3. So that is the Hermitian of this matrix. Now inner product of x and y is x Hermitian y. So this is called inner product. If we evaluate the Hermitian of x and multiply it with new another matrix y, that is called as inner product of x and y. And if the inner product of x and y is equal to 0, it means these two vectors x and y are orthogonal vectors. So orthogonal vectors are x and y. Now this is one definition. X second norm square is equal to x Hermitian y. This is one property. So by mistake I have written x Hermitian y. In fact it is x Hermitian x, right? So x second norm square is equal to x Hermitian x. This is another property. A B whole Hermitian is equal to B Hermitian A Hermitian. And if we take the Hermitian of a matrix and that becomes equal to the original matrix, then that matrix is called as Hermitian matrix, right? So the Hermitian of A is equal to 2, 3 minus 3 iota, 3 plus 3 iota, and 5 iota. So let's evaluate the conjugate of this matrix. So it that the conjugate will be equal to 3 minus 3 plus 3 iota and 3 minus 3 iota. Then take the transpose of this matrix. So this 3 minus 3 iota will come over here and that 3 plus 3 iota will come over here and we will get the same matrix. So if the Hermitian of a matrix is equal to the original matrix, then that matrix is called as Hermitian matrix. So if we have a Hermitian matrix, right? So if A is equal to a Hermitian, then every eigenvalue is a real number, right? So this is an example of a Hermitian matrix. Now, if you evaluate the eigenvalues of this matrix, you will see that lambda 1 is equal to 8, and the second eigenvalue lambda 2 is equal to minus 1. So these two eigenvalues are real numbers. So this is another important property. And two eigenvectors of a Hermitian matrix are orthogonal to each other. This is another important property. The two eigenvectors of a Hermitian matrix are always orthogonal to each other. Now we have two complex vectors, x and y. This is x, this is y. And x Hermitian multiplied by y is equal to 0. And y Hermitian x is also equal to 0. So if we have such a case, then x and y matrices are orthogonal to each other. So this is the property which we have studied over here. So if x Hermitian y is equal to 0, then x and y are orthogonal vectors. So this is the example. Now, if x Hermitian is equal to minus x, that is called as skew Hermitian matrix x. Then x matrix will be skew Hermitian. Like in the previous case, we studied that if x transpose is equal to minus x or A transpose is equal to minus A, then the A matrix is called as skew symmetric matrix. Similarly, if A Hermitian is equal to minus A, then A matrix is called as skew Hermitian matrix, right? Now, finally, we will discuss the unitary matrix. So that the definition of a unitary matrix is that if U Hermitian multiplied by U is equal to identity matrix, or U multiplied by U Hermitian is equal to the identity matrix, then that matrix is called as unitary matrix. And in that case, U Hermitian is equal to U inverse. So this is the definition of a unitary matrix. And that is all about our today's lecture on complex matrices, and we discussed some important properties, and we validated those properties with the solved examples. And I hope you have enjoyed this lecture. For watching more videos, please subscribe this channel. Until the next lecture, it's goodbye.